it's like, I mean, there's so many circuit boards. I'm not complaining about it. No. But the FFQ one, that was kind of chill. Did you also have to, like, make that? Does everyone get the same one, or is it? I'm not sure, because I swear I saw them the other 125, so I swear I saw them end up cheap with like.
Or to rubric.
I wish I got it. No, I know. When I got it, like, there's like a yeah, exactly. And I was like, ooh. I think I did it last one. Oh yeah, it was kind of the back. I think I did every back. Dude, if I did it, I'd be lighter. It's like, I don't know. I didn't study the July very much. So I was like, that was nice. I mean, like, I forgot that. Very good. More now. You guys believe that we can have both the quiz and the exam next week in one time? Yeah. But the quiz is this. Or is it the test? Is it this one? I think so. I don't think it is. I thought the most test is. And then the quiz on. It's from what I remember when I was looking at it. Yeah, that's kind of. There's the test is we have a test and then we have a week of classes and then like the final. Yeah, which is also really scary. I feel like it would have made more sense if they just made this test like last year. It would just be a yeah. They could have added it. I figure really good. That's so much.
Okay, guys, don't forget to do attendance 1322. It's a code. And let's get started. Everything okay? That's fine. Is it recording? Okay, let's get started. Today we're gonna finish this chapter 4 with talking about control hazard. So the code 1322. If you need it, write it or whatever. I can write it here too. One, 3, 2, 2. Okay. So anyway, so we already talked about hazards, pipeline, but so far we know how processor works. We had some abstraction layers that we started from, and then we talk about performance, how we can check the performance, and then talk about instruction set architecture. And we said the instruction set architecture is like a interface between software and hardware. And we moved to processor design. We learned how we can design a processor that can work in one cycle. We call that one cycle processor. And we implemented that in actually hardware description language for your first project. And then we said how we can improve the processor. We said one of the ways pipeline, and but pipeline is great. It can actually make clock per instruction as low as possible. to increase performance. The lowest one is 1. We want to make it 1. That's a dream that we always have when we design processor, but it's not always happening. Why? Because of hazards. Hazards happening. We have different type of hazard. We talked about that last few sessions. And today we're gonna talk about control hazard as the last part of processor design. And we're gonna move to new chapter that is related to memory. We are finishing processor and we want to go for memory. We're going to introduce memory hierarchy. So how we actually design the memory, because memory also has some kind of design. Memory has different layers, different speed, different actually size. So you want to always have the highest speed and highest volume of space, but is not possible because they are contradict each other. We want to see how we can design the CPU, design the memory, that we call that memory hierarchy. How design that, how manage that to programmer thinking that access to highest volume of space at the same time highest speed. So how we can do that, we're going to see that. That's a very good good topic. We're going to start it today. So before going to the memory hierarchy, we need to know some extra stuff in hazard. Last class we started, we've actually finished the class with showing how we can implement hazard in a hardware level. So hazard need to get detected first. That's the main part. So you need to detect hazard. Is not complicated. In a instruction decode part, you just can check if the previous destination is equal to source of this instruction. This is hazard. So you can recognize that. Even in a very low, you easily can check those. And if this happens, you can detect hazard. So to check hazard, you need to have a control part in your CPU just responsible for detecting hazard. And then detect hazard, you can act different ways. And normally, a stall works for all the hazards. You just can give a stall. And we have different type of stall. Some stall keep the instruction, don't remove everything. Some kind of stall need to flush the pipeline, make everything 0. So for this type of stall is for load use hazard. Remember in load use? So you need to put one stall between to can make that happen. Even though you did forwarding, still that's not gonna save the problem because you need to move backward. So to solve that, we can do a stall. How we can detect that stall? We can detect dependency in an instruction decode. And if this is the load and has this problem, we need to do it. But the instruction is okay. We don't need to flush the pipeline. Instruction, the next instruction is okay. It's not the wrong instruction, but we just need to make one delay. We just need to make one delay. How we can make that? We need to freeze the pipeline. How we can freeze the pipeline? We can make a program counter write 0. Also, we can make pipeline register regarding to instruction fetch, instruction decode, also 0 to freeze the pipeline. This is freezing. Freezing means the information is there, but we can't write any. We made the control signal for this register 0, because you know that registers they have some control signals. One of them is write. Can we write something on it? Another one is a clear. If we put the clear signal 1, it's going to get 0. We might have more control signals for some specific actually registers, but write is one of them. PC write is for program counter. IFID write is for IFIR pipeline register. So we are doing pipeline. We have some registers to transfer information inside the pipeline to keep them to the other instruction going to override them. We need to keep them. That's the point. So that's called freezing instruction, fetch and decode. This is for fetch and decode. But for execution, execution still is working. So we need to put something there too. What we're going to do? 0. We're just going to put, for the control part, we're just going to insert bubble or no operation. What is no operation? We're just going to put 0. We're going to see the hardware soon. So for decode, for fetch and decode, we do program counter 0, freeze, and for the rest is just inserting no operation to the execution part. This type of stall is for load store. We have other type of stall that we're gonna see. For example, flush the pipeline. We're gonna see that. So the pipeline behavior instructions before hazard continue normally, and the dependent instruction is delayed by 1 cycle. So because we wanted 1 cycle delay, but we're gonna execute the next one. We just freeze it and then execute it next clock. So this is the hardware we last time we talked about that. As you can see, we have a new part in this structure, in this data path, that this new structure is kind of checking if the hazard happening or not. How we can check it? You can check these registers, input registers, or source registers, and these destination registers coming from here. Somewhere I need to follow this, is coming from here. The destination coming from here and the source coming from here. If there is equality here, you're going to see the code soon. In that case, we're going to make program counter write 0, instruction fetch write 0. Also, we can make this multiplexer 1 to just let 0 get executed, 0 as a no operation. When we put 0 in a control part, it means no operation. It's not going to do anything. And whatever happening here, because all of these control signals are 0, write back is 0, memory read write 0, execution, everything 0, so it's not going to do anything. You're just going to waste 1 time. 1 clock here going to get wasted. This type of stall happening for load use hazard. Load use hazard when you have load instruction and add, subtract, whatever after. Any question about this? How we can implement it in Verilog? You just need to find if this is happening, like when execution destination, this is execution destination, is equal to one of the sources. So this means you have exactly dependency. That's checking dependency. And what's going to happen? Program counter write is 0, IFIR write is 0, and control max is this one, is 1. Control max is 1. Instead of getting from control unit, we get everything 0. All the control signals gonna get 0. And all the control signals get 0 means inserting no operation or bubble. So this is one of the methods that you can implement a stall using hardware. You're doing a stall with hardware. You're just wasting 1 clock physically in computer, when you are checking if there is a time that you need to put a stall there, you just freeze everything. How freeze them? With putting program counter right 0 and IFID right also 0. This is freezing these two parts. Freezing means you keep whatever were there before, we keep them, we not reset them, we don't clear them, we keep them for the next time, for the another step, next step. And to put no op operation or no operation instruction, we just put control, make all the control signals 0. How we can do that? You just can have a multiplexer. You need to add this new multiplexer here. And it has two choices. One bus coming from the controller, another bus coming from just 0. And when this is happening, they all gonna get 0. That's called inserting no operation. Okay, that's how we can implement hazard in general. Okay, let's do this eye clicker to see how we can deal with jumping. Because in jumping, we have some issues. Okay, let I active this. Oh, I need to log in. Need a little time, but you can read the question first. I need to connect. Okay. So we have this this piece of instructions, jump and link and add. But is there dependency here? Can you see any dependency? Any dependency? Okay. We don't have dependency here in the way that we had it in data hazard. You can connect now, but I'm going to explain it a little bit. So we have a jump and link. First of all, what kind of control is that? Is it conditional or unconditional? Jump and link. Is that conditional or unconditional? We have two kinds of jump. One kind of jump is conditional. So we check something, and if it's true, we jump. Unconditional means we don't jump, we don't check anything, we just jump to the target address. Is this one, jump and link, conditional or unconditional? What do you think? Unconditional, yes, because we're not checking anything, we just jump. And that x0 is for return address. You just gonna keep that, but this x0 is just to be 0. We don't want to use it. Anyway, this is not unconditional. Sometimes in some computers, there is a pseudo instruction called J. It means jump. J target. Instead of writing that, you can have that pseudo instruction. Pseudo instruction is not a real instruction. The assembler put that instead to make programmer easier to understand and use it. And we have this and add. There is no register in command. There is no dependency in that case. But this is kind of hazard. We want to see, I ask you, the processor is like before, 5-stage. And to understand this is a jump and link, we need to understand it in decode part, instruction decode. As if you know that, what happened to the add? It executes normally because jump and link is unconditional. It is stalled until the jump target is known, and it is flush, turned into no operation, and it is forwarded to the next stage without change. Which one is your choice? Let's see. We had, yeah, mostly you selected C. It is flushed, not stalled. So it executes normally. For sure, it's not execute normally because you're jumping somewhere. We are jumping somewhere, but the 3 instructions under jump is also inside the pipeline. If this jump happening, that is always happening because it's unconditional, this instruction need to go to garbage. We're not gonna use them anymore. We can't use them anymore. And because we're gonna jump somewhere else. Yeah, if the jump is exactly the next, that's not happening because you don't want to jump to the next instruction. So don't jump at all then. So you are jumping somewhere else. It's not the next instruction. Anyway, so it executes normally. No, that's not right. It is stalled. Yeah, we need to put a stall here, but it is stalled until the jump target is known. That makes a little thing. So can we stall to understand this is jump? Because when we understand this is jump in decode, but when we decode, we already fetch the next, and we realize, oh my God, this is a jump. So is in decode, we understand the next instruction, this is a jump. So the next instruction is already decoded, already fetched. So if we do a stall, if we consider a stall as the last slide, that we need to keep that instruction inside, that's not true. But what about the flush? Yeah, we need to flush because we already have something here that is wrong. We can't come back and run add again. Add is a wrong one because we want to jump to target. We are not going to run add anymore. So that's the wrong one. So it is flush. So this is different between flush and stall. We're going to talk about this difference as well. And turn that to no operation. So whatever was add here, we made it no operation physically. Like with the hardware, we can do that. And it is a software. Oh, sorry. It is forward to the next stage without change. So that's also wrong. So the best answer, most of you guys did correct, is the C. C is the correct answer. We need to flush. That's the difference between a stall that happening in data hazard and a stall that happening in actually control hazard. In control hazard, most of the time, we have something wrong inside the pipeline, and we need to flush it. Flush means you just made 0. It's a wrong instruction. We're not supposed to run it at all. So that's different between flush and normal stall, that we're going to see that later. Okay, so the correct, and let I close this. Okay, and this, okay, good, is C. This is the correct answer. And the reason is that when we are instruction fetch, instruction decode, execution, and memory, and write back, and next instruction fetch, instruction decode, and rest. So this is the jump and link, x0 and target, and this is add, x5, x1, x2. So there is no dependency, but because of this jump, you have another kind of problem, and that's a control hazard. And the control hazard, when you understand, you normally, when you fetch it, you don't understand that this is jump. You understand that this is jump when you decode it. When you decode that, controller can understand, oh, this is a jump. So here you understand this is jump, but you already fetch something wrong. You need to jump, but you fetch something that is not related. So you need to flush this. You need to make everything 0. And that's, you can't solve it without stall. It's no possible to fix it. That's one of the issues that we have with control hazard. But the good news is it's not that often in the computer. The control hazard is not that often, but data hazard happening a lot. That's why using forwarding is a good way to fix the data hazard. So that's control hazard. So control hazard happening in two different situations, sometimes unconditional, like jump and link, or jump and link. What was the other one? Jump and link are, I forgot. Anyway, these two both are unconditional. It's kind of jump or return, sorry, jump and link return. When you are at the end of the function, you want to jump back. Okay, so both of them, because they don't have a condition, you're just going to jump and without any condition. This is unconditional. In unconditioned jump, you just need to put one stall. The type of stall that I talked to you is a flush stall. You need to flush one instruction and just make everything 0. For branch is different because it's conditional. Sometimes happening, sometimes not. Here we just consider branch equal or branch not equal, but we can have more instructions. But anyway, branch equal, for example, is one of the instructions. If 2 registers are equal, then we jump. Other than that, we are not jumping. So, but in which stage we understand that the jump happening or not? In which stage? Fetch, decode, execute, or write back. In which of this stage we understand that branch is happening or not? Because branch normally check 2 registers. If they are equal, they jump. This equality, we can check this equality in fetch. We can check this equality in decode. What about decode? Can we check? Normally, no, because checking equality need ILU to subtract them to each other. If the 0 is 1, it means they are equal. So normally execution. So normally this, you understand the jump happening in execution. You already have 2 instructions in pipeline, and when it's happened, you just need to flush everything, flush these 2 instructions. But there is some method to fix it. We're going to see that. We can kind of predict it, or we can sometimes do it in advance. Check if they are equal in advance. We can see that later. I mean, next slide. Slide. So the point is, the next instruction may be wrong. I'm not saying the next instruction need to get delayed. I'm saying it's wrong. Completely is not supposed to be in a pipeline. That's the difference between flush and stall in terms of freezing. So the solution is this. For both cases, we can do a stall. A stall can be happening with hardware or software, like compiler or assembler or programmer even can fix that. We can have flush, so remove wrong instruction. So in the first one, imagine we understand, I mean, software understand that this is one of those, jump and branch. So immediately put a no operation after. In jump, put 1. In branch, put 2. Done. Very easy. So the compiler easily can find and fix everything. Flush can happen with the hardware part. For flush, you can do different way. So we can remove wrong instruction from the, because it's already something wrong inside. In the first one, the compiler can detect and not gonna let anything wrong go inside the pipeline. But here, imagine something wrong is there, so we can flush it. We're gonna see hardware and other examples. And another way that this is interesting is that what about we are make decision earlier. Instead of checking in execution that these two registers are equal, we can go one step ahead. We can check it when we decode. When we decode, we have those information. We can just check them if they are equal. If they are not equal, we can go ahead. We're gonna, with this early decision, instead of having two in branch, we can have one. We can get less than one. We always need one, because one is, you need to jump anyway. You need to jump anyway. I mean, if you do this part, the branch becomes jump. Branch becomes jump. Conditional becomes unconditional, and unconditional always have one delay. Okay, I don't want to make it too complex, but let's see in this. Let's see example or difference between so this flush, especially jump hazard and flush. So jump hazard. So jump decision, you understand when you jump in this part. When you do decode, you're checking registers and read registers. So in decode, you actually understand that this is jump. So the next instruction is wrong anyway, because you're jumping. That's for unconditional. So you need to flush. How we flush? Two things. First of all, we put flush 1. If flush, instruction fetch flush 1. And in this case, you need to clear everything. So everything means even make this, you need to make instruction fetch, instruction decode, instruction 0. And also you can make all the control signals also 0. Control signals is also, control signal 0 means no operation, no op. So pipeline effect. So one incorrect instructions removed and one cycle penalty. So you are kind of flushing here, and whatever was here gets 0. This get all 0, and the controller also gonna make 0, and everything gonna get normal. So this is example jump target. This is pseudo instruction. We don't have this. We have an add after. So the add is a wrong instruction, need to get flushed. And in Verilog, how we can implement it, you just need to check if flush is happening, instruction fetch flush happening. You just need to put instruction fetch instruction. I wrote here instruction fetch ID, instruction fetch instruction code register. That is for pipeline register. It's actually this register. 32 all binary zeros, so it means no operation. And otherwise, we need to put instruction there, because we always keep the instruction there. We need it later because we're going to overwrite it. So this is how we are doing unconditional jump, how you are managing unconditional jump in RISC-V, how we do flush. Flushing happening like that. Flushing happening with this instruction. Put everything 0. However, this also can happen when you put the control signal related to clear, we have also clear as a control signal. We also can put that one, but also we can just put 0, assign 0 inside that, same. Okay, so this was something let's go for branch in Verilog. How we do branch in Verilog? So one of the things that in branch we can do, as I mentioned, is to detect branch earlier. There is another method that is like a probabilistic method. We are predicting the outcome. So we say, okay, we did many tests and we realized, okay, most of the jumps happening. So or not happening, for example, most of the jumps not happening. So we consider one of these cases, and probabilistic, we consider probabilistic, and we say, okay, we're gonna say, okay, the jump is not happening. So we go to the pipeline, and when we detect it, we flush. So this is another method that's called predict its outcome. So we have two methods to fix it. One that is actually has more overhead and faster is like resolve the branch earlier. So when we can detect the branch in instruction decode, so we can detect and resolve branch in instruction decode, because in instruction decode operands are in hand. So operands are in hand, you can check them if they are equal. So it means the detection or the branch happening. So when the branch happening, we just need to put one, we just need to do one flush. And so this is very good. So in Verilog, this is how we are detecting that. We are saying, okay, is the branch equal, for example? If this is branch equal, and register instruction fetch source 1 and instruction decode source 2 are equal. When they are equal means we need to do jump. So this is showing take branch. So the take branch is going to be 0 or 1, is a binary. So if it's 0 means it's not happening. If it's 1, it means we're going to take branch. So we can understand that using Verilog easy. And if this is happening, what we need to do, we need to flush instruction fetch instruction decode and insert no operation. And update the program counter to the new target. Where is a new target? In a target. When we have branch, we have a target too. So we move the program counter to that. So that's how we are dealing with the resolve the branch early. So this is how we deal with that. Actually, the code for the rest is also here. When we want to take the branch, if we are not taking branch, we are normally doing, if we are not taking the branch, we are, what we are doing, if we don't take the branch, we are doing normally, we are getting the program counter and take that, that's a fetch, and we increase this. Other than that, what we are doing, we are putting no op in, no op is all 0. We put all 0 there and make the new program counter based on the target. The good point in a hardware description language is it's like a programming. You're doing very complex things just with this, and when it's compiled, you can put that in a hardware and works very good. Yes, so this is what we are doing with resolve the branch early. What about this prediction one? The prediction one, as I mentioned, you consider one case more likely. In most of the systems, not taken is often more likely. Okay. You're going to consider one of the case more likely, most of the time not taken. So when it's not taken, means put everything inside pipeline. So they continue fetching next instruction easily like a normal way. And sometime we're going to recognize, oh, the condition not happen. Even though we consider not taken, we realize that the condition is happening. When we understand that in execution part, we understand that in execution time, but two instruction is already inside. So in this case, we need to flush them all. So early detection, early decision, reduce penalty from 2 to 1, and prediction keeps pipeline running. But if the condition taken, if the branch taken, you need to flush to how? Like this. The next slide. This is how we do that. So we need to do 2 flush. And this is happening when we are using a stall for branch. So that was something that we should know about pipeline and hazards. So this chapter is almost done. Any question about this type of control hazard? We are moving to something different a little bit. We just have one project related to this that, as I mentioned last class, is a designing processor using pipeline. That the code is already existing in your book. You just need to make that, to run that. It's not complex. It's very, but you need to understand it as well. You need to, I'm going to ask you some questions about that as well. That's it. Okay, so let's go fast. Any question? Go a little start about, oh, it's nothing, about memory hierarchy. So we have right now CPU designed, but the CPU that we designed in this class, the memory was inside CPU. We just considered multiple registers, packed them, and made like a matrix of registers, or the vector of registers to make memory. And that's an inside CPU, and that's the fastest CPU ever. But you are limited. You can make your memory big. But programmers want to have large memory. You always want to have large memory. Some applications really need big memories. And also we want to be fast too, not just large, but fast as well. But these two are a little contradict each other. So if something is fast, it's slow. You always know. And if something is small, it's fast. At the same time, something that is small, something that is fast is expensive too. So you need to kind of find the way that how we can at the same time have very fast access, but large volume of memory. So this is, as I mentioned, is like a contradiction or illusion. But how we can do that? What about we use different type of memories, and we kind of write a system to make this illusion for the programmer that has lots of memory but doesn't have. It just have, for example, a small piece that is very fast, close to CPU, and use that all the time. But at the same time, those are connected to each other. Like, for example, you have processor here and one register file here. And then outside of the CPU, you have, for example, a static RAM that is very fast. And then under that, you have a dynamic RAM, DRAM, that is bigger and then, for example, you have, hard drive or magnetic disk that is very big. So that's like a very large. But when you are going down, the size get bigger, and when you go up, it becomes faster and smaller. But if programmer just working with that fast one, programmer thinking that, but they are all connected. There is a system for memory management, a system managing everything here. So what about we have like this? Programmer thinking, oh, is working with a very fast memory, but at the same time, we are just make this illusion for programmer, and the system manage everything. When programmer wants to access something that is not there and is here, it's just bring it there. And it's kind of probabilistic, but need to have some rules. And the rules called locality. We have a rules in memory management called locality. So we have different type of locality. We're going to see that's the things that help us to can design actually memory or memory hierarchy or the levels of memory. But the idea is to access a small portion of the memory very fast, and at the same time you are thinking that you have all the things available. So the idea is something that called locality, as I mentioned. We have two principles of locality that all of the memory management is based on these two rules. The first is temporal locality. Temporal locality is saying that if you access a part of the memory in a time t, you're probably going to access that again in time t plus 1. So it's better to be in hand, to be in a top layer, to be in cache, to be in CPU. That's called temporal locality. Time, temporal means time. So we have temporal logic, for example. Is not the same, but I just wanted to mention temporal means time. So it means if you access something now, you probably is so likely to access that again. This is called temporal locality. If you access something now, you're going to access that again. What about a spatial locality? A spatial locality is saying if you access something in a memory or instruction, now you're probably going to access surrounding that memory or instruction as well. What about bring those two? Not just bring that one, bring surrounding, like 2-3 instruction before and 2-3 instruction after, and put them in the somewhere close to CPU to access that faster. These two principles makes memory management, makes this illusion works well. When you are a programmer, you don't feel it. You just think, oh, it's so fast. But under that, so many things happening, all probabilistic. They are just bringing, blocks or lines. We have some unit of information moving from here to here all the time to make this illusion happen. To just you think that you access with a very high speed, but at reality is not true. So that's the main point. So the key message is that we design memory based on how programs behave, not worst case scenarios. So it's like a probabilistic a little bit. Okay, so the idea is this level of memory. We have one unit, this unit called block or line. Sometimes we call it line. So it can be like a matrix of blocks that when you are close to CPU, so this is getting smaller. When you get in lower levels, this block is bigger. I mean, block the set of blocks. The block is the same size. Is multiple actually word. like 4 words or more, 16 words. It depends. And the unit of data transfer is block. Sometimes we call it line, and may contain multiple words. Multiple word in that block, but it's just transferring all the time. Another thing that happening is something that we call it hit. Hit, and hit like a probability of you want something and be there. It means hit happened. So hit, when data is in hand, when data is in the memory that you are reading, hit happening. And you can guess that if it's not happening, miss happening. So we have hit and miss. Everything in this memory management system is based on these two type of probability or ratio, hit ratio and miss ratio. And they are a complete space. So it means if it's not, if you have hit, you can find miss. 1 minus hit is miss. So miss ratio is 1 minus hit ratio. So hit ratio means in, for example, how many access you got a hit. For example, you are in your computer, the size of the memory is the way that when you are accessing to the cache, for example, 1/4 times, you have a chance to access your data. So hit is going to be 1 after maximum 4 access. So in that case, you can say hit ratio is 1/4. And then miss is 1 minus 1/4, so 3/4. Yes, it's more, 3/4. So this is hit and miss. But what's happening after miss? So the processor checking the cache here, for example, this is cache or SRAM, static RAM. It's check this and it's not there. So what we need to do, we need to bring whatever we wanted here based on the locality rules. Not just that, maybe surrounding, also bring it in hand. And that's is after miss. So data data is brought to upper levels and future accesses becomes faster. That's the main idea. So we have different type of memory. We have a SRAM, static, dynamic. We have magnetic. They have different speed, as you can see, nanosecond, like 50 times less, and that's millisecond. So it's a lot less. And okay, so next class we're going to continue. Memory management is very good topics, and we're going to see that application for computer. Any questions? Okay, have a good day.